All right. Hi, everyone. My name is Brandon Cao, and I'm from the Material Science Engineering Department. And I worked on kind of an interdisciplinary project with physiology. And today I want to talk to you about cardiomyocytes, or heart muscle cells, and how they remodel in heart disease. So heart disease is a leading cause of death in the world, and there's a variety of medical risk factors, but the physiological mechanism is really unclear, especially at the cellular level. And because of this, it's difficult to develop specific and targeted treatments for patients. So the aspect of heart disease we want to look at is the mechanical environment. And so in heart disease, these collagen fibers proliferate, and this makes the extracellular matrix stiffer. This matrix is what connects cardiomyocytes to each other, and so when this matrix stiffens, the cardiomyocytes are constrained and also can't contract as well. So that's difficult for the patient. So people have been trying to model this kind of matrix stiffening for many years, and they've used these polymer substrates to do this. And they've shown that differences in substrate stiffness can actually cause changes in the cell properties that they're cultured on. So for instance, in these cells, muscle force generation as well as actin fiber alignment are both affected. But the thing is, with these experiments, mostly neonatal cardiomyocytes are used. But adult cardiomyocytes, which are more physiologically relevant, is what we want to study. So these experiments also mostly use static substrates. So you either have a stiff gel or a soft gel. And this is not as useful of a system because cell remodeling is really a dynamic process. So these findings have been limited. And there have been ways to kind of get around this using extra steps and different methods, but this just adds more variability to your experiment. So our goal is to develop a material system that can dynamically change stiffness so we can better use these materials to understand the changes in cardiomyocyte properties. So I looked at 3 different materials. First was these polyacrylamide gels. Second were these UV tunable PDMS, and also looked at magnetic elastomers. So using these substrates, we then cultured cardiomyocytes on top of them and looked at their responses. So the first material I looked at were these UV cross-linkable polyacrylamide gels. And the idea was to add this HMBP photo cross-linker to the polyacrylamide, and the vinyl group would incorporate into the backbone of the polyacrylamide. And when I shine UV on it, the side chains would cross-link to each other, and this stiffens the entire material. I ran into a few problems, though. So the solubility between these monomers, the catalyst, and the solvents didn't really go well. And even when I changed the composition of the solvent, I got a really inconsistent kind of volume. So when I stored these in liquid, they would swell up to 300%. And also the unpolymerized polymers were toxic to cells. So we ultimately moved on from these polyacrylamide to these more stable PDMS. So these are made in 2 different steps. First is this platinum-assisted cross-linking, and this makes the base kind of soft PDMS. And I can use a AFM, or an atomic force microscope, to kind of indent the surface of this material and get the stiffness or the modulus of these materials. So the second step was a UV stiffening. So when I shine UV on it, I activate this DNPA, which is a photo initiator, to cause the thiolene side chains to cross-link to each other, and this stiffens the entire material. So with an increase in UV exposure time, we see an increase in the stiffness up to 10 times the original. We just chose a 90-second exposure time for our experiments to get a significant modulus increase without causing significant UV damage to the cells. So here it just shows that with a 90-second exposure, we see a big increase in the modulus. And over 48 hours, when stored in 37-degree liquid media, that it's relatively stable over time. So we also made these control PDMS. So these are materials that don't have the DNPA photo initiator, and we show that with UV exposure and with time in culture that these materials stay relatively stable as well. So then we moved on to these magnetic rheological elastomers, or MREs. So how these work is a magnet is put under the material, and the magnetic field aligns the iron particles that are inside this PDMS. So this stiffens the material. But when I tried to measure the stiffness with the AFM, I got a really non-significant modulus increase. And we think that this is because of the surface roughness on this the MRU with the magnets. And because our probe is only about 40 microns in diameter, this is smaller than the feature size on these materials, and this makes the contact area inconsistent, and thus our measurements inconsistent over here. So we were able to work with a collaborator, and using a larger cylindrical probe that probed deeper into the material so that you don't feel the surface roughness anymore, we got a 5 times increase in the modulus. So now that we've identified these two materials, UV tunable PDMS and these MREs as materials that can quickly and significantly increase their stiffness, we want to actually use them to measure changes in cardiomyocytes. So we looked at the stiffness change as well as the cytoskeleton organization. So here's how we measure the stiffness of the cardiomyocytes. Basically the same setup, but these live cells are cultured on the PDMS, and the UV comes from below and the AFM comes from on top, as you see here, to measure the stiffness of the cell. So it's important to understand cardiomyocyte stiffness because it's a metric that's elevated in heart disease, and basically stiffer cells cannot contract as well. So here's our data when cells are cultured on either the stiffened PDMS in red or the control PDMS in black. So the modulus for both groups increases with time, but it increases more in the control group. And so kind of zooming out and comparing these modulus values to the original PDMS stiffness values, we think that the cells are trying to remodel to match the substrate stiffness. So the black's trying to match the black, and the red's trying to match the red. But the stiffened PDMS in red is just so much stiffer than the cardiomyocytes themselves that the cells can't really respond. And so that's something we really want to look into further, is whether we can lower the base modulus of these PDMS materials and see if we get a different response. But that's all we did with cardiomyocyte stiffness. Now we want to look at the morphology and the cytoskeleton changes in these cells. So how we did this was we took a confocal microscope slide of these cells, and using ImageJ, running filters and turning these into a binary mask, we can fit these particles to ellipses and then find the dimensions of these cells. So we compared cells that were cultured just kind of sitting in a glass dish for 48 hours, and also those that were attached to these MREs, either with or without the magnet. And what we found was that after culturing on the MREs, the major axis was shrinking, and the minor axis was increasing. So this means that the cells are kind of getting shorter and wider. So this is really similar to something we see in a type of heart disease called hypertrophic remodeling. So in normal hearts, you have the heart chamber that's pumping blood. And in hypertrophic remodeling, basically the walls of the chamber are getting thicker. And this means that there's less volume for the heart to pump blood. We also looked at these detyrossinated microtubules. So microtubules are a really important cytoskeleton fiber inside your cells, and they can either be tyrossinated, so with this tyrosine residue on the end, or detyrossinated. So we can stain these with antibodies and use immunofluorescence microscopy to visualize these. And what you need to know is that D-tier microtubules are stiffer, and they're more common in heart disease because they actually inhibit the contraction of the cells. So comparing cells that were cultured on the soft or the stiff MREs, we see that there's a higher network density of these D-tier microtubules when the cells are cultured on a stiff MRE. So this kind of implies that just a change in the external environment of these cells can really affect the internal organization of these cells in ways that are similar to disease. So we also want to quantify this microtubule network increase, and so we convert them to binary masks and can calculate the % area coverage of the microtubules. And here's our data. So we can see that with the magnet, the D-tier microtubule cell area coverage increases. The D-tier to total microtubule ratio also increases, but the total microtubule content is relatively stable. So this means that any increase in the D-tier microtubule content is due to a shift from the tier microtubules to D-tier, and not an increase in the overall kind of microtubule content. And this gives us another insight into how diseased hearts get these D-tier microtubules in disease. So just to conclude, we have characterized the stable and rapid modulus increases in PDMS, so a 10 times increase in stiffness and a 5 times increase in stiffness in these magnetic elastomers. And using these materials, we've shown a causative link between the external mechanical environment and actual cardiomyocyte properties. So we see changes in cardiomyocyte stiffness, hypertrophic remodeling, as well as microtubule network remodeling, all in ways that are similar to heart disease. So hopefully this information gives us a better idea of the mechanism and will be useful in developing more specific and targeted therapeutics that can improve patient quality of life. Thank you. Yeah, happy to take any questions. Sure, yeah. So like I said, the current materials that are being used are mostly static, so they don't have this kind of stiffness increase. So that means you really have to compare two different populations of cells, while we can just plate the cells on top and then measure their properties and then increase the stiffness and then measure it again. So that's kind of the improvement on the materials front. In terms of the cells that are being studied, neonatal cells are mostly being studied, so those are much more easier to work with, but these adult cardiomyocytes are really kind of more interesting to medicine. So we're the first to show these stiffness increases and these changes in the cytoskeleton reorganization in adult cardiomyocytes.
What applications of this are you most excited to see?
For me, I think that it's really far down the line, but I really want to see kind of if this can translate into some type of application in medicine. So possibly changing kind of the collagen fibers, if decreasing the stiffness of the kind of the cell tissue or the heart tissue can change the function of the heart, especially in the actual muscle cells. So.
How far away do you think we are from that?
I don't know, because our lab doesn't really work that far into the kind of the stream, but I don't know. Yeah, probably a decade.